probably one of the most underappreciated tactics that a mathematician has in his toolkit is the idea of curve sketching. So when presented with an arbitrary function, there are a number of techniques that can be taken to determine what that function looks like. And in the age of technology, in the age of great visualizations, it's a well-founded question. Why should we study this? Why should it matter at all how to graph a function? If I'm given a function, I can plug it into a computer and I can get an answer. Why should I care about curve sketching? And that's a legitimate criticism. The answer to that is twofold. One is that you're not really always there with technology, which is kind of not a great reason. But the second one is the intuition that's there. So the idea of being able to use these techniques and write them down is that eventually you get to a point where you don't have to write them down. You become fluent enough with these techniques and the methods in calculus of differentiation that you can look at a function and you can immediately see sort of breaking points where the function starts to change its behaviors, and you can analyze its end behavior such that when you see a function, you're not scared of it. You can understand a lot about it. Now, graphing techniques help, but that intuition carries beyond simple sketching. It carries on into when you start to move into functions of multiple dimensions and things that become harder to visualize. Using these techniques how to solve and how to probe at those to construct or maybe manipulate. And to that point about construction, you can even construct functions that satisfy certain properties, because you know that if you want something to have a critical point at a certain value, you can design it to have a critical point at a certain value. But only if you understand the curve sketching techniques are you going to be able to easily construct functions that satisfy certain properties. So I would like to encourage you to really absorb what's happening here and understand that it's very, very useful in practice. So there's really a 10-step process, and there's always little nuances that can make you better, but these 10 steps are very important to graphing a function. The first is to find the domain and range. You've been finding the domain and range in your studies for a long time. And remember, the domain is just what are the possible inputs to this function. What is not allowed is one of the things you should search for, like, we can't divide by 0, we can't take the square root of a negative number, points like that. The second one is the range. What are the actual possible outputs of the function? When you look at it, does it have a constrained range? Do those ranges go off to infinity? Which comes into play here as well. The next thing is to find the Y-intercept. This is probably the easiest. If you have a function that's a function of x, you simply plug in 0 for x. Whatever the output is, that's the Y-intercept. Remember, the Y-intercept is the point where x is 0. The second thing is the X-intercepts, if they exist. X-intercepts don't always exist. Think of like a sine wave that's 2 steps above, or 2 units above the axis. It will waver, but it never crosses the x-axis. It just does this and bounces above it. So for finding the x-intercepts, what you do is you set the function equal to 0 and solve for what inputs, and you might have multiple that cause that would cause that function to be equal, to have an output of 0. So that can be a little more complicated, but ultimately it's algorithmic. The next one is probably one of the more useful ones, but is not strictly necessary. And it's this idea of symmetry. So if we take an even function, what that means is that if you plug in a negative value, you get the same thing as if you plug in a positive value. So the way you do that is you plug negative x into the function, and if all those negatives vanish, or at least the function looks the same after you simplify it, then you know it's an even function. The reason that's important is because then I can look at just the right side. If I plot just the positive values, I can then just take it and fold it over, and the negative version looks exactly the same. So I only have to do basically half the work. The next thing is one for odd functions, which is if you plug in a negative value, you get the opposite of what happens when you plug in a positive value. So if you plug in a negative x, when you simplify it, you get the original function with just a negative factored out of that function. If that's true, what you get is something that has this 180-degree rotation over the origin. Another way that that's represented is a reflection across the line y equals x. So instead of a reflection across the y-axis, you get a reflection across y equals x. So if this was the y-axis, if something was here, it gets reflected down to here and whatnot. But it might be easier to think of it as a rotation of 180 degrees. Whatever suits you better. But again, if something's an odd function, it means you can graph just the positive side and then take that and reflect it to get or rotate it to get the negative side. So you're saving yourself some effort. You're having to do a little effort here, but potentially saving yourself on the end. And the key with even and odd functions is usually you can, once you've got a good eye for it, you can start spotting it early and go, oh, well, that's an even function. And you don't have to go through this whole rigorous process. And finally, there's periodic functions. What a periodic function simply means is that at every interval of a certain length. So, for instance, like for the sine function, it's 2 pi. Every 2 pi, the pattern starts over. So it starts here, 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 here. And that period may be longer or shorter depending on what type of function you're dealing with. But the reason why periodic behavior is really nice for symmetry is that if it is periodic, that means that you only need to graph one of those periods, and then you can just repeat it. You can just put it forward, put it back, all the way across its domain. So periodic functions are really nice because you don't have to work that hard for them. The next pieces are, these are the sort of the calculus pieces. These are really the pre-calculus pieces. These are the calculus pieces. Well, not so much vertical asymptotes. Vertical asymptotes happen when you try to go towards a value and that limit approaches positive or negative infinity. So in some ways it's calculus, but some people will have studied this in pre-calculus course. And what happens is as the input approaches a finite value, the function starts becoming unbounded, either towards positive or negative infinity. So if that happens, you're going to have a vertical asymptote. These are harder to spot, but they typically happen at places where the function gets divided by 0. That's a pretty common one. If you're dealing with logarithmic functions, they also have an asymptote, a vertical asymptote. So that's those are kind of the keys. Really, it's usually when there's a possibility of 0 in the denominator. It's not always true because it might be a removable discontinuity, but if it's not a removable discontinuity, usually you have vertical asymptote. So the next one are horizontal and slant asymptotes. Now, horizontal asymptote, what happens is you take the function and you try to plug in positive infinity and negative infinity into it. And if you plug in positive infinity and you take the limit, and that a limit approaches a finite value, right? It could be 0, could be -1, could be 1 million. Doesn't matter. If it approaches a finite value, you can draw that dashed line because the function will approach that. Now, it doesn't always approach like this. Sometimes it approaches like this and kind of wobbles out. Generally speaking, well, not generally. Vertical asymptotes, the function will not cross. But horizontal asymptotes, the function can actually cross the asymptote, and that's okay. It also has a slant asymptote if when you are taking that limit, the function actually starts to resemble a line. So that happens when it's a polynomial. It can happen in other cases, but generally speaking, when you have a polynomial on top of another polynomial, and the polynomial on top is 1 degree larger, exactly 1 degree larger than the one below, then what you'll have is it kind of all divides out, and you have something that's kind of a function of like an mx plus b situation, and it will, it'll still shoot off to infinity, but it actually sort of rides a line. So slant asymptotes, depending on who you ask, don't matter, because it technically is not a horizontal asymptote. It's just saying that it doesn't shoot off like any particular function, it just resembles a line as it goes up. So most of the time, concern yourself really only with horizontal asymptotes. The next pieces are, very strict calculus pieces because they involve derivatives. This one is the intervals of increase and decrease. So what you're going to do is you're going to take the derivative of the function, and what you're going to do is you're going to segment the function into places where it's positive and places where it's strictly negative. And while you're at it, you're going to get values where it's equal to 0. So that's real. These go hand in hand because you're going to find the critical points, because there's going to be points where the first derivative is 0, and if it's not 0 at some point, it has to be positive or it has to be negative, right? Because those are your only options, positive, negative, or 0. So usually it actually makes more sense to start here, find your critical points. That will segment or partition your domain into strict pieces that you can say, all right, in this piece outside the critical point, the derivative is positive. In this piece, it's negative. In this piece, it's positive. So you can use that to show if the derivative is positive, the function is increasing. If the derivative negative, the function is decreasing. But you can also use the first or second derivative test. Now remember, the first derivative test says you take a critical point and then you look at the first derivative to the left and the first derivative to the right. And if it's increasing on the left and decreasing on the right, then it must be a maximum. If it's decreasing on the left and increasing on the right, it must be a minimum. You can have situations where that just doesn't happen. Think like a asymptote where it comes up and then also comes up. So it goes up to the asymptote and up. So there's really no maximum at all or minimum. It's doing this. Now the second derivative test, remember, that's when we take the second derivative of the function and evaluate it at the critical point. And if it's negative, that's that concave down, so that tells me that I have a maximum. If it's positive, that's that concave up, so it tells me it's a minimum. So anyway, these two go together, and these two go together. So what you want to do is you want to find a point of inflection. That's going to happen in two cases. One is where the second derivative is equal to 0. 2 is where the second derivative fails to exist. Now, let me be clear. Just because either of these is true doesn't mean you have a point of inflection. It just means these are the places you check. So you take the second derivative, you check where it's 0, you check where it doesn't exist, then you say, okay, these are places where the concavity might have changed. So again, it partitions the input into places where you go, okay, it's concave up, it's concave down, and so on. So going up to here, outside the points of inflection, right, outside those points, you just say, all right, if the second derivative is greater than 0 on this interval, it's concave up. If the second derivative is less than 0 on this interval, it's concave down. So what you're going to end up doing in all these cases is you're going to go through the sort of the standard pre-calculus set. Then you're going to take limits, first derivative, second derivative. So you're going to have to do a lot of steps. Curve sketching is not fast. It takes a while. Now, when you're good at it, it doesn't take very long at all. When you get really, really good at this stuff and really comfortable with derivatives, it goes pretty quickly. But until then, it does not. You are going to have to work at it to be good at this. You can't just do 2 examples and be done with it. You're going to have to do a lot to be good at curve sketching. But it's a skill that's really going to pay dividends, because being able to visualize functions very quickly and understand their behavior adds a lot of insight and offloads a lot in your working memory so that you can focus on the problem at hand instead of having to think about what the graph looks like.